Hello, we are Team 13, and this is the final presentation of our analysis and redesign of a commercial blender. First, we'll go over which product we chose in its product family, and then we'll go over various aspects of its assembly and how changes we made to the design optimize its production. So this is the blender we chose. Like most blenders, it has spinning blades in a jar, and when they're sold at $90, roughly 110,000 of these are sold to household consumers per year, which are our primary customers, and then our secondary customers are restaurants and cafes, and roughly 20,000 of these are sold per year to them. These are the two assemblies that describe it, and we've split it up into the jar and base. This is the fast diagram that describes the functions of it, with our primary function being blending food on the left, and the secondary functions that comprise it being in the middle. The two assembly sequences that we came up with are bottom up and top down, where the bottom up starts with the bottom housing, and it works its way up to the jar and the lid. And then the top down sequence analysis starts with the lid, and then it works its way down to the base. We chose the first sequence of assembly because it was more efficient. This is the function component matching matrix, which we took the functions from our fast diagram and listed the components vertically. Every component has a function, and we made sure that one function is not met by more than 40% of parts. This is our bill of materials, and we've come up with a total cost of $54.9. This is the quad chart that indicated which parts of this we needed to optimize for DfM, so I'll show you. These are the product family design parts, and this basically tells us how the different modules are going to accommodate the different consumer groups. And these are the two variants for the jar, and these are the two variants for the mixers.
Original assembly diagram of the blender with the different variants of the blades and jar without accounting for product differentiation delay. As one can see, the different variants occur within the middle of the assembly diagram, thus leading to variations of the products occurring early on. Assembly diagram to delay product differentiation, as this will reduce lead time in creating different products. The jar and blade variants are incorporated almost at the end of the assembly process, causing this to simplify the manufacturing process as all the variants are at the end.
This is our manual assembly time calculation for the primary product variant. The total time comes out to be 88.02 seconds, and the assembly efficiency is calculated to be 64.76%. For design for manual assembly, the platform part chosen for improvement is the bottom container. First, we can change the number of fins from 5 to 3, as you can see from the left picture to the right picture, effectively increasing the part symmetry and removing complexity. Next, we can add thin extrudes to the opposite end of the container so that it is easier to orient without the fins in view. Finally, we can add rounds to allow for easier insertion into the slots. The module part chosen for improvement is the agitator blades. As shown, there are previously 3 individual blades that are mounted onto the agitator base using an M5 screw. We can reduce the assembly time by making this only one blade, reducing the number of parts. We can increase the symmetry of the part by making the blade symmetric across 3 planes. Finally, allowing the blade to have bent features prevents any further adjustments being made to the part. As you can see from these changes, the insertion time of the bottom container is reduced to 4.5 seconds, and the insertion time of the agitator blades is reduced to 4 seconds. This gives us a 5-second reduction in total assembly time to 83.02 seconds and an increase in efficiency to 68.66%. As you can see, there is no change in the functionality of either part resulting from the improvements. Regarding manufacturing cost, there is an insignificant change in manufacturing cost due to approximately equal removal and addition of material. The cost of the agitator blades, however, decreases due to the reduction in material and the number of parts.
For the automatic assembly analysis, the team considered the subassembly with the platform part being the new bottom container, the drive stud, and a slinger. When considering the orientation efficiency, the relative handling cost, the max feed rate, the handling cost from that max feed rate, the relative workhead cost, and the insertion cost, the team realized that the total assembly cost for the subassembly is $1.697. Optimized assembly, the team combined a drive stud and slinger to make one part following DFA 1. Using DFA 13, the team was able to eliminate the clearance between the stud shaft and the slinger bore. And using DFA 8, the team was able to ensure that the geometry change avoided nesting of the slingers when stacked up when prepared for assembly. After reanalyzing the subassembly, the team realized that the total assembly cost had dropped to $1.248. The team realized that the functionality likely does not change, but the manufacturing cost likely increases due to geometry complexity.
For the bottom container, we are considering the reliability and repeatability of fitment of the container into the upper housing. The most important dimensions for this are the 120-degree angle between fins, which has a fairly low tolerance of ±2 degrees. The outer diameter of the container allows for the agitator assembly and jar to fit on top. ±1 millimeter is sufficient for this. This fitment is necessary for containing the mixture and preventing any spilling due to misalignment, as shown by our functional component matching matrix. These are the compatible manufacturing processes given our material and shape of part. Second, these are the compatible processes given our mass and economic batch size of 100,000 units per year. Finally, we can narrow down to conventional machining or injection molding using ABS from our tolerance and surface roughness charts.
The critical dimensions and tolerances for the agitator blades are shown here, with the most critical dimensions being the through hole for the fastener and the bend radius and normal blade length and width of the overall part, which are critical for the maximum coverage of breaking down the components. The purpose of the agitator blades, to reiterate again, is to break down the components and facilitate cleaning. Shown here are the compatible manufacturing processes for the given material and shape of the part, the compatible processes for the given mass and economic batch size, and here are the compatible processes for the given tolerance and surface roughness. The recommended process is sheet metal work, and the recommended material is stainless steel.
The bottom container for assembly, we then designed it for manufacturing by calculating the cost of injection molding. Here are the calculations along with the assumptions. After doing the injection molding calculations, we then placed the bottom container object or part into the DfM pros. We were given recommendations to reduce the cost of injection molding. Some included removing the undercuts, which will remove the side posts necessary. Others included adding draft angles. And one final suggestion was to change the maximum wall thickness and reduce it. From this, we were able to make changes and modifications of the design leading to this engineering drawing. This drawing shows all the key dimensions that we had changed. One important dimension to note is that we reduced the maximum wall thickness from 5mm to 4mm. The design for injection molding guidelines 1 through 6, excluding 5 to make the modifications for the bottom container. First, we minimized the wall thickness from 5mm to 4mm to keep uniform wall thickness. This also allows us to cut costs on the cycle time because the piece will cool down faster. Secondly, we added a draft angle to allow for mold release while also adding a fillet radius to avoid sharp corners. Lastly, we removed the undercuts such that side posts were not necessary for our part and thus reducing the mold cost. All in all, by reducing the thickness and getting rid of the side posts that were necessary, we were able to reduce the cost of the mold, ultimately bringing the cost of the piece from 75 cents to 53 cents per part. Additionally, these modifications did not affect the functionality of the part, but it may lead to increase in assembly costs due to a lack of undercuts.
In addition to the bottom container, we also performed DfM analysis on the agitator blades. The selected process for the stainless steel part was sheet metal working. Some of the assumptions and the equation used are shown here. The key assumption was that this part would be stamped using 4 dies, with the operations being piercing, blanking, bending 2 blades up, and bending 2 blades down. The material, operating die, and total costs are shown in the table on the right, and the total cost per part is about 75 cents. We ran this part using DfM Pro for stamping, which found errors such as bends not being in the same direction and the bend radius being too small. These changes were made as shown in the engineering drawing on the right. As shown, many of the changes made to the agitator blade design were based on DFSM standards. The sharp inner corners were removed as per DFSM 6 and 9. The 2 downward bending blades now bend up as per DFSM 2 to minimize steps and remove the need for the second bending die. And the bend radius was increased to be greater than the part thickness as per DFSM 8. These changes also reduced the operating cost and die cost as shown. This is primarily due to the elimination of the 4th die, which is needed to bend 2 of the blades down. Overall, the manufacturing cost was reduced by around 9 cents, and the assembly cost would also decrease since it is now easier to identify insertion orientation. The functionality of the blade would be worsened when it comes to breaking down components and improved when it comes to facilitating cleaning. To wrap up the analysis on the agitator blades, both designs were submitted to hubs to estimate the cost per part if 110,000 units were ordered. The plots used for extrapolation are shown, and we accounted for an assumed 20% profit in hubs quote. Shown at the bottom are the costs we obtained from our DfM analysis and the hubs costs for both designs. Note that the hubs costs are under 50% of the DfM costs, which could be a result of bulk material discounts and reducing the piercing and blinking operations to a single die. For our product service system, we have an app with a monthly subscription plan for smoothie and baked goods recipes for $5 a month. The app would also allow customers to order replacement parts for their blenders or rent new modules on a use basis. Overall, this would improve the customer experience and have a positive environmental impact as shown. To conclude our analysis and redesign of the Oster Pro 1200 blender, we were able to improve ease of assembly and part manufacturability. The costs were reduced through both DFA and DFM efforts as shown. To critique our design, we reduced part count and decreased assembly time and cost. However, this was done at the cost of some part functionality, and there are still some parts that require redesign. If we were able to redo this project, we would pick a less optimized device so there would be more room for improvement and design a simpler secondary variant.